Out in the silent, fathomless dark between the ghost light of distant galaxies lies a monster. It is an object of such profound contradiction it borders on the impossible. It is a star that has died, yet it screams with more energy than 1,000 of our living suns. It is the size of a city, yet it weighs more than all of humanity's creations combined, multiplied by 1 billion. And from its crushed, spinning heart it unleashes a tempest. This is no ordinary terrestrial gale of moving air. This is a phantom hurricane, a cosmic outflow of pure force and exotic matter rushing into the void at nearly the speed of light. For decades, we thought we understood this celestial phenomenon. We had models, elegant equations that described its fury. But the cosmos, in its infinite and humbling wisdom, has shown us we were only scratching the surface. Deep within this ethereal torrent, astronomers have now detected a secret, an anomaly, so profound it challenges the very bedrock of our physics. This is the story of a dead star's bizarre wind, and how its high-energy secrets are forcing us to rewrite our understanding of the universe itself. To comprehend this enigma, we must first journey back to its crucible, to the most violent event the universe can offer, the death of a giant. Imagine a star many times more massive than our own sun. For millions of years, it has been a stately luminous sphere, a nuclear furnace fusing hydrogen into helium and then helium into carbon, on and on up the periodic table. It forges the elements of life in its sweltering core. But this process of creation cannot last forever. Eventually, the star creates iron, the ultimate stellar ash. Fusing iron consumes energy rather than releasing it. The delicate balance between the outward push of fusion and the inward crush of gravity is catastrophically broken. In less than a second, the star's colossal core, once thousands of kilometers wide, collapses under its own stupendous weight. The implosion is cataclysmic, a runaway gravitational collapse that slams protons and electrons together with unimaginable force. They merge their identities, erased, becoming a sea of neutral particles, neutrons. The core, now barely 20 kilometers across, becomes a single gigantic atomic nucleus, a substance so dense it defies all earthly intuition. This sudden halt of the collapse triggers a rebound shockwave of titanic proportions. The wave rips through the star's outer layers, blasting them into space in a supernova explosion, a conflagration that can outshine its entire galaxy for a few brilliant weeks. Left behind in the expanding, incandescent debris cloud is the relic. The city-sized, ultradense remnant, the neutron star. The sheer density of this object is a concept our minds struggle to contain. It is a reality so alien, so compressed that analogies become our only guide. Imagine taking Mount Everest, that titanic pyramid of rock and ice, and grinding it down, crushing it with a force beyond all reckoning. Imagine squeezing every single atom, collapsing the sacred space that defines their very existence, until that entire mountain range, all 9,000 meters of it, is compressed into a space no larger than a sugar cube. Now take another mountain, and another. Take all the mountains on Earth, every peak and every range, and crush them into that same thimble-sized volume. You are only just beginning to approach the material density of a neutron star. A single teaspoon of its substance would weigh 10 billion tons. This stellar corpse is born spinning a legacy of its parent star's slow rotation. Think of a figure skater. As she pulls her arms in, her spin accelerates dramatically. This is a fundamental law of physics called the conservation of angular momentum. The neutron star is the cosmic expression of this principle taken to its extreme. A star that once took weeks to complete a single rotation is now crushed into a sphere 1,000,000 times smaller. Its rotational speed becomes blistering meteoric. Many of these stellar cinders rotate hundreds of times every single second. They are cosmic flywheels of unimaginable mass and velocity. And they are not just spinning, they are magnetized. The parent star's magnetic field, also compressed into this tiny volume, is amplified to a staggering intensity. The magnetic field of a neutron star is 1 trillion times stronger than Earth's. It is a force so potent it would warp the atoms in your body from meters away, a field that dominates its environment for millions of kilometers in every direction. This combination, a super-dense, hyper-fast spinning sphere with a colossal magnetic field, creates one of the most extreme engines in the known universe. It becomes what astronomers call a pulsar. The discovery of these objects was not a sudden revelation, but a slow, creeping realization that the universe harbored entities far stranger than we had ever dared to dream. The idea was first born in theory in the minds of two brilliant astronomers, Walter Baade and Fritz Zwicky, in 1934. Observing a recent supernova, they made a breathtaking intellectual leap. They proposed that these explosions created a new type of object, a star composed almost entirely of tightly packed neutrons. For over 30 years, their idea remained a fascinating but unproven piece of theoretical physics. A ghost in the mathematical machine. Then in 1,967 inches, the damp fields of Cambridge, England, a graduate student named Jocelyn Bell Burnell was monitoring data from a newly built radio telescope. She was hunting for quasars, the bright hearts of distant galaxies. Instead, she found something else. A signal. It was a faint, rhythmic pulse arriving with a regularity so precise, so clock-like, it seemed utterly unnatural. It pulsed once every 1.337 seconds, a cosmic metronome of perfect cadence. Puzzled, the team first considered terrestrial interference. When that was ruled out, they half-jokingly nicknamed the signal LGM, one for little green men. Could it be an extraterrestrial beacon, a message from another civilization? The truth, when it was finally pieced together, was in some ways even more profound. This was not a message, it was a lighthouse, a natural cosmic lighthouse. They had found Baade and Zwicky's theoretical ghost. The signal was from a rapidly spinning neutron star, its powerful magnetic poles sweeping through space like a searchlight beam. Each time the beam swept past Earth, our radio telescopes registered a pulse. They had discovered a pulsar. Humanity had its first tangible proof that these impossible objects were real. And with this discovery came the first hints of the stellar wind. This is not a wind of gas or air. It has no temperature in the conventional sense. It is a torrent of charged particles born from the very fabric of space-time around the spinning magnetic colossus. The process of its creation is a masterclass in extreme physics. The pulsar's dizzying rotation combined with its titanic magnetic field induces an electric field on its surface of almost unimaginable power. This electrical force is so strong it literally rips particles, electrons and protons from the neutron star's crust. It flings them out along the magnetic field lines. But this is only the beginning of the story. These initial particles are accelerated to phenomenal speeds, approaching the universal speed limit, the velocity of light itself. As they are whipped around by the magnetic field, they radiate high-energy photons, gamma rays of incredible potency. And here something magical happens, a process predicted by Einstein's E equals mc squared. These gamma rays, carriers of pure energy, interact with the magnetic field and transform. Energy becomes mass. Each high-energy photon spontaneously splits, converting into a pair of particles, an electron, a particle of matter, and a positron, its antimatter twin. The vacuum of space itself is being boiled into a fog of matter and antimatter. Imagine a colossal city-sized garden sprinkler, but one of impossible design. Instead of a gentle rotation, it spins 700 times per second. Instead of flinging out droplets of water, it hurls torrents of electrons and positrons. This particle stream, this mixture of matter and antimatter we call a plasma, is then caught by the pulsar's rotating magnetic field lines. The field acts like a slingshot, grabbing this plasma and flinging it outwards into interstellar space with ferocious momentum. This relativistic outflow is the pulsar wind. It is an ethereal hurricane, a constant stream of high-velocity emissions flowing away from the dead star, carrying away its immense rotational energy. For eons, the pulsar spins down infinitesimally slowly, its rotational vitality converted into this perpetual invisible gale. For decades, this wind remained largely a theoretical construct. We could infer its existence from the slowdown of pulsars, but we couldn't see it directly. It is, after all, a tenuous stream of subatomic particles spread over vast distances. Seeing it would be like trying to see the wind on Earth by looking for individual air molecules. But we can see its effects. When this ultra-fast particle torrent smashes into the surrounding interstellar medium, the thin gas and dust between the stars, often the remnants of the supernova that created the pulsar in the first place, it creates a spectacular structure, a cosmic crash site known as a pulsar wind nebula. The wind, traveling at nearly the speed of light, hits the slower-moving gas and creates an enormous shock wave called the termination shock. At this boundary, the particles are violently decelerated, releasing their kinetic energy as a brilliant glow of radiation, particularly in high-energy X-rays and gamma rays. The most famous of these is the Crab Nebula, the beautiful ghostly remnant of a supernova witnessed by Chinese astronomers in the year 1054. At its heart beats the Crab pulsar, a neutron star spinning 30 times a second. For centuries we saw the nebula's glowing filaments of gas. But when we looked with modern X-ray telescopes like NASA's Chandra X-ray Observatory, we saw something new, something breathtaking. We witnessed the wind made visible. Chandra's images revealed a stunning nested structure of rings and jets emanating from the central pulsar, a celestial bullseye. This is the termination shock, the place where the pulsar's bizarre wind collides with the universe around it. We could see the wind's energy lighting up the nebula from the inside out, like a lantern placed within a cloud of smoke. The images showed a torus, a donut-shaped structure of emission encircling the pulsar's equator, and perpendicular to this ring, two magnificent ghostly jets of matter and energy were seen erupting from the pulsar's poles, stretching for light years into space. It was a portrait of cosmic power, the direct visualization of the pulsar's invisible gale. Our models seemed to work beautifully. The physics was elegant and it matched observation. We believed we finally understood the nature of these stellar tempests. We were wrong. The universe, it seems, always has another layer of complexity, another surprise in store. Recent, more detailed observations of other pulsars have begun to unravel this tidy picture. Astronomers focus their instruments on a pulsar named PSR B900 and 6-49, a spinning relic located thousands of light years from Earth. Using advanced techniques to study the polarization of the light from its nebula, they were attempting to map the magnetic field structure within the outflow. What they found was perplexing. The models predicted a relatively smooth, well-behaved stream of electrons and their antimatter counterparts. The reality was far stranger and far more energetic. The data revealed that this pulsar's wind was not just a simple plasma. It was heavy. Somehow, in addition to the expected lightweight electrons and positrons, the wind was carrying along much heavier particles, protons and atomic nuclei. This was a discovery that sent shockwaves through the astrophysics community. It was like discovering that a gentle breeze was somehow capable of carrying solid iron cannonballs. The established theories simply could not account for it. The electric fields at the pulsar's surface, while immense, were thought to be capable of lifting only the lightest particles. Ripping entire atomic nuclei from the crust of a neutron star, an object with a surface gravity 200 billion times that of Earth, should be almost impossible. And even if they could be lifted, how were they being accelerated to such enormous relativistic velocities within the particle torrent? The elegant sprinkler analogy was beginning to break down. The dead star's gale was not just a simple spray of antimatter, it was a complex, powerful, and deeply mysterious cosmic river, carrying material that by all rights should have remained locked away on the stellar surface. The physics was incomplete. The textbooks needed a new chapter. This single bizarre observation throws open a Pandora's box of profound questions and forces us to explore new radical ideas about the inner workings of these cosmic behemoths. How is this heavy wind being generated? One leading hypothesis involves a violent phenomenon known as magnetic reconnection. Imagine the magnetic field lines emanating from the pulsar not as static, rigid structures, but as dynamic, twisting cosmic rubber bands. As the neutron star rotates, these field lines become incredibly tangled and stressed, storing up phenomenal amounts of energy. Periodically, these overstressed field lines can spontaneously snap and reconfigure themselves into a simpler, lower energy state. This event is explosive. The stored magnetic energy is released in a sudden, violent burst, a magnetic detonation that could be powerful enough to ablate or blast away heavier material from the crust, injecting it directly into the outflowing wind. We see a similar, though far less powerful process on our own sun, where it creates solar flares. On a neutron star, such an event would be a tempest of unimaginable ferocity. Another avenue of inquiry looks not to the magnetic field but to the star itself. Perhaps the crust of the neutron star is not the perfectly smooth, solid sphere we once imagined. Perhaps it is a dynamic, evolving landscape racked by starquakes. The immense stresses within the ultradense crust caused by the interplay of rotation and magnetic fields could cause it to crack and buckle. These seismic events on a neutron star would release more energy than 1 trillion of Earth's most powerful earthquakes. Such a cataclysm could fracture the surface venting reservoirs of heavier ions from just below the crust, feeding them into the path of the emerging particle stream. The wind then is not just a surface effect, but a sign of geological turmoil deep within the stellar remnant. And then there is the most exotic possibility of all. Perhaps our fundamental understanding of what a neutron star is made of is wrong. Our models tell us they are composed of neutrons. But under such extreme pressures and densities, physics predicts that even neutrons themselves might break down. Their constituent particles, the quarks and gluons, could be liberated, forming a new bizarre state of matter called a quark-gluon plasma, or strange matter. If the heart of a pulsar is a core of this strange quark matter, its surface properties and its interactions with magnetic fields could be completely different from what we expect. The heavy wind might not be an anomaly at all, but the natural signature of a star made of something far more fundamental and alien than simple neutrons. This bizarre wind could be our first direct observational window into the realm of quantum chromodynamics, the theory of the strong nuclear force playing out on a stellar scale. The implications of this discovery ripple outwards, far beyond the study of pulsars. For decades, we have been puzzled by the origin of high-energy cosmic rays. These are single subatomic particles, often protons or heavy nuclei, that constantly bombard Earth from deep space. They travel at almost the speed of light, and carry more kinetic energy than a tennis ball served by a professional player. Where do they get this incredible acceleration? Supernova explosions have long been the prime suspect, but now these heavy pulsar winds offer a tantalizing new possibility. Perhaps these bizarre stellar gales are a primary source acting as natural particle accelerators, churning out and flinging a cocktail of charged particles across the galaxy. The wind from a single neutron star could be seeding its entire galactic neighborhood with the building blocks of cosmic radiation. By studying these winds, we may finally solve one of the longest-standing mysteries in astrophysics. Furthermore, this discovery forces us to reconsider the entire life cycle of matter in the universe. We know that supernovae forge and distribute heavy elements. Now it appears that the stellar corpses left behind continue this process, but in a much stranger way. They are not just passive cooling cinders. They are active engines of cosmic recycling, slowly but surely eroding themselves, casting their own exotic substance back out into the cosmos through these peculiar winds. The universe is more interconnected, more dynamic than we ever knew. The death of a star is not an endpoint, but a transformation into a new kind of active, creative, and profoundly powerful object. The quest to understand this phenomenon is now driving the development of the next generation of observatories. Future space telescopes with unprecedented sensitivity in the X-ray and gamma-ray spectrum will be designed to dissect these winds with surgical precision. They will map their composition, measure their velocity, and trace their magnetic structures in exquisite detail. We will move from detecting anomalies to creating a full atlas of stellar outflows, comparing and contrasting the winds from different types of neutron stars, from young energetic pulsars to ancient slowly spinning ones, and even to their hypermagnetic cousins, the magnetars. Each one will provide another piece of this grand cosmic puzzle. And what of the far future? What do these winds tell us about the ultimate fate of these extraordinary objects? As a pulsar ages, its rotation slows, its energy reserves dwindle, and its wind inevitably weakens. After millions or tens of millions of years, its lighthouse beam will fade, and its particle gale will subside to a mere whisper. The stellar remnant will become a cold, dark, quiet sphere of neutronium, drifting silently through the galactic graveyard. But some of these objects are not alone. They are locked in binary pairs, orbiting another neutron star or a black hole. As they spiral closer together over billions of years, their final moments will be anything but quiet. They will collide in an event known as a kilonova, an explosion of such violence. It rips the very fabric of space-time, sending out gravitational waves. In this final desperate cataclysm, the neutron stars are torn apart, their hyperdense matter, including the exotic nuclei, once carried on their winds, is cast out, seeding the cosmos with the heaviest elements like gold and platinum. The material of the star, once a mystery hidden in an enigmatic wind, becomes the raw substance for future generations of stars, planets, and perhaps life. We began this journey in the dark, contemplating a monster. But what we have found is not a monster, but a magnificent, intricate machine. The bizarre wind of a neutron star is a testament to the universe's boundless creativity. It is a phenomenon that connects the quantum world of subatomic particles with the grand astrophysical scale of stars and galaxies. It is a puzzle that pushes our theories to their breaking points and beyond, forcing us to confront the humbling reality that our knowledge is a tiny island in a vast, unexplored ocean of cosmic truth. The secrets being carried on this high-energy torrent are not just about dead stars. They are about the fundamental nature of matter, the origins of cosmic radiation, and the engine of creation that churns at the heart of the most extreme environments the universe has to offer. The wind is blowing, carrying whispers from a realm of physics we are only just beginning to comprehend. And our journey as scientists and as a species is to simply stand, look up, and learn how to listen.
Particles breach the star's corona, they instantly accelerate to 99 point speed of light.